Hello everyone, my name is Rhea and I'm happy to talk to you about the topological hybridization of Magnons and Magnon bound pairs. This work was done in collaboration with Alexander Moog from the University of Mainz in Germany and Jelena Klinovaya and Daniel Oss from the University of Basel in Switzerland. This project was motivated by the work by Bayedal in 2021, where the authors did a neutron scattering experiment with iron diiodide, which is an antiferromagnet, and they uncovered the hybridization of a 1 Magnon state with a 2 Magnon bound state. In a neutron scattering experiment, one shoots a neutron onto a sample, and the neutron interacts with the bulk matter of the sample, and then the neutron is sent out again. What is observed is the change in momentum and energy of the neutron due to the interaction with the sample. In this figure, we see the change in energy, or energy transfer, as a function of the change in momentum, or momentum transfer, in terms of intensities. The more yellow, the higher the intensity of the change. The hybridization of the single and 2 Magnon bound state leads to this band gap opening throughout the Brillouin zone, which is this dark line between the two yellow lines. This phenomenon cannot be explained with linear spin wave theory, like we see here in this numerical simulation on the right. There, the gap does not show up and we only see the single Magnon state. The goal of this project is to answer the general theoretical question of how to describe such a hybridization of a single Magnon state with a 2 Magnon bound state. On top of that, we want to investigate if the avoided crossings can be topologically non-trivial. This means that there can be edge states between the bands that are topologically protected. I first want to give you an understanding of the terms single Magnon and 2 Magnon bound states. Consider a simple nearest neighbor exchange Hamiltonian on a square lattice with a negative exchange integral J, which is ferromagnetic. In this figure, consider only the white spheres with the arrows pointing up, representing the fully polarized ground state of a ferromagnet in z direction. Usually, the magnetic excitation of lowest energy above this ground state is made of 1 spin deviation relative to said ground state. The eigenstate of such a spin deviation is a superposition of local spin flips, like this red arrow here, pointing in the opposite direction than the other spins. Classically, this is a spin wave, so a phase difference between neighboring precessing spins, here seen from a side view and from a top view. The quantized version of this is called a Magnon, which is a bosonic quasi-particle. We describe the center of mass momentum K with a Bloch state of a flipped spin at the lattice side RL. This represents our eigenstate of the single Magnon. If we now add another spin deviation to the lattice, we call that a 2 Magnon state. This is a superposition of many such double spin deviations. We can describe them in a similar way to the single Magnon state, with K as the center of mass momentum and R as a relative distance between the flipped spins in real space. Now, if two Magnons are close to each other, the energy penalty to flip those spins is lower than when they are far apart. They are known to form bound pairs or so-called bound states. This happens because the attractive interaction lowers the energy of the bound state. This would be described by the state K, A, with A being the lattice constant. These bound states are described quantum mechanically since they disappear in the classical limit, so when the spin quantum number S goes to infinity. The requirements that are necessary for such a topological hybridization of single and 2 Magnon bound states are the following. First, we need ferromagnetism, so a fully polarized ground state, so that a Chern insulating phase is allowed. In this example, a square lattice. Additionally, we need strong spin anisotropies to isolate the single and 2 Magnon bound states. Then we need the single and 2 Magnon bound states to cross in energy at some point in the Brillouin zone. To open a band gap, we need to break spin conservation. To make the band gap topologically non-trivial, so that it can host edge states, we additionally have to break an effective time reversal symmetry. We achieve both of these points by including an antisymmetric exchange interaction, the Rhea interaction. These 4 steps are necessary to open a topologically non-trivial anticrossing in the dispersion relation of our system, meaning that edge states are able to appear. The bands are being equipped with a Bari curvature, which is this object omega here, which is used to describe a topological invariant called the Chern number. Following the recipe we just established with a spin 1/2 square lattice model with first and third nearest neighbor Heisenberg interactions, with strong Ising anisotropies, a magnetic field, and the Diemer interaction, we make a nanoribbon projection of a specific energy interval of our band structure, where we assume periodic boundary conditions in x direction and open boundary conditions in y direction. Indeed, we see that there is an edge state connecting the two bands. We observe 2 energy modes, one with positive group velocity and one with negative group velocity. These modes are edge localized. This means that they live on the left and the right edge of our sample, which can be seen here in terms of probability amplitudes. The edge states are a genuine quantum effect, since the bound states disappear in the classical limit, and with them the topological chiral edge states. To summarize and conclude, we have seen that the spin non-conservative interactions can generate topological chiral edge hybrids of Magnons and Magnon-bound pairs. For this, we need the following recipe. We need ferromagnetism with strong spin anisotropies. We need an energetic crossing of single and two Magnon bound states. We need the breaking of spin conservation, and we need the breaking of an effective time reversal symmetry. If you're interested in what changes on different lattices, or with the spin 1 model, or if you're curious how this phenomenon contributes to the thermal Hall effect, then please have a look at our article. Thank you for your attention.